Hey guys, Sebastian from Madrigal here, and welcome to part 9 of the video series where we create a Vulkan renderer for the basis game engine. We have, according to my calculations, 4 classes left to implement before we are able to render things. So they would be the shader program, the texture sampler, the pipeline state, as it's called, and the render context. And the pipeline state and render context, they're quite large, quite complicated things to set up, and they probably will warrant their own separate video. But I was thinking today we would try to get the shader program and the texture sampler set up. So let's start with the texture sampler, because this is pretty simple. So VEZ doesn't really do anything for samplers. Oh, if we look at samplers, it simply says that sampler creation and usage in VEZ is identical to Vulkan. And probably the reason why they didn't do anything to the sampler API is that it was pretty easy to use to begin with. So let's have a quick look at how samplers look in Metal, shall we? So texture sampler Metal, open that up, and we can open up the implementation here on the other side. So yeah, samplers are pretty simple, it would seem, in all rendering APIs. So essentially we just have one big method here called init, which sets everything up, and then you create a sampler state, and in destroy we destroy the sampler state. That's essentially it. And then the renderer actually uses this get metal sampler state here to return it. And in Vulkan we don't have a metal sampler state. Instead we have a VK sampler. So VK sampler, and just call this VK sampler. And as we do with all classes, essentially we have this render device VK, so device VK, and what was it called? We have ves.h conveniently open here on the side. So let's have a quick look at sampler. Right, ves sampler create info. Here we go. So we're going to want to have one of these guys. Don't necessarily need to keep it as a member, but I'll do that for now. And then we'll want to have the same kind of getter that we had in Metal as well, so we can actually get to this actual Vulkan sampler, right? So get VK sampler. It could essentially just as easily be a public member. I should probably actually just remove the private parts here, because yeah, encapsulating them like this is not necessarily needed, especially since this is like an implementation in a plugin, so there's no real reason to do any of this. But yeah, let's leave that for another day. Okay, so we go to the implementation side, and we look here at what we have on this guy. Oh, actually, before we do anything, we want to initialize our things. So go to device and VK sampler. This would be VK null handle, and now we can start filling in this create info. So let's start by initializing it to 0, essentially. Then we can simply start here by doing mCreateInfo mag filter, and we should have get texture filter, and desk is called mag filter here as well. Yes. So once again, this is part of the type conversions VK, this big file that I essentially haven't touched since my last attempt at using Vulkan, and it just converts all these enums from a basis enum into a Vulkan enum, and we can use the same thing here. Right, so that's a mag filter. Then we have the min filter, so magnification and minification filters. And we have the MIP map mode, and that would be get MIP map mode, and I think it's called MIP map filter. Yes, MIP map filter, and create info address mode U, and this is of course not super interesting. I'll try to get this done as quickly as possible. UVW, still hopefully not making any mistakes. I would hope we could actually avoid that. Right, UVW MIP LOD bias. Okay. That's a float, so do we have something like that? MIP LOD bias, yes we do. I have to admit that I don't know exactly what all of these things do. I think we can, well, MIP LOD bias, that's kind of self-explanatory, but I haven't really ever used anything like that, like pushing and pulling MIP levels further or closer. So so we don't have like any boolean like this, but what we can probably do is if this is larger than 1, then we do like a VK true, else we do a VK false, and then it had the max anisotropy, and that would be just the float like that. Oh, it's actually, yeah, it's a float. Interestingly, it's a float. This is like an uint, yeah. Okay, that's probably fine. Then we have compare enable, and this would be comparison enabled, right? That's a bool. I don't know if like these VK bools are sort of, you could probably just cast it to one of those. You don't have to do this part, but let's leave it in for now. Compare op, that would be get comparison function. Yes, it's just called comparison op in Vulkan terms. Comparison func. My conversions are there. These functions, they're sort of named after the DirectX terminologies or the terms most of the time. So yeah, that's they might differ a little bit from the Vulkan ones. I think that would be like minlod, otherwise it's 0. Then we can copy this guy, and we can do a maxlod, and we can do a maxlod, minlod, maxlod. Okay, border color. What the hell is this? VK border color. It's not actually a color. It's just a selection. some of these. I'll put it to opaque black for now. I don't exactly know what would be the best value. Unnormalized coordinates is probably just VK false. I've never used anything like that. Yeah, like I think in here we actually have a color value. You can set in DirectX. You can set a color as an actual color, and here you can only have like a few select choices. But nah, it's probably fine. Okay, so that should be everything we need. So we have mag, min, mipmap mode, UVW, miplot bias, anisotropy, and max anisotropy, compare, enable, compare, op, minlod, maxlod, border color, and unnormalized coordinates. Yes. Okay. So now that we have this, I think we should be able to just create a sampler. So do result, and then we do BEZ, create sampler. Yes. Get VK device, and this would be the address of create info, and this would be the address of the sampler itself. Yes. So VEZ, much like Vulkan itself, is nice in the sense that these methods, these functions, they all pretty much follow the same kind of naming convention, and I would assume this returns a VK result, and it does. And in the similar vein, you can guess that there would be like a VEZ destroy sampler, right? Which we can use in exactly the same way. Like so, and then we can set this to VK null handle, just in case. Okay. And this should be everything we need, actually, and we are probably already creating these guys. So if we launch the game now, and we see here, we get to this point, and our create info is filled in, and it looks pretty good. And if we run this, we get VK success. Cool. So that's sampler. That was an easy one. So the next thing would be the shader, and it should be a little more involved, but perhaps not that complicated. So let's have a quick look at the metal one again. So we have shader program metal. Put these headers on the right side and implementation on the left side. Okay, so how you actually do these things, how you actually use shaders, obviously depend on the API quite a bit. Metal only has, as far as I know, vertex, pixel, and compute shaders. I haven't actually used compute shaders on Metal. I just have this here as a commented out thing. But yeah, we'll probably support all the, well, except the compute shader part probably, but we'll support all the shaders in the graphics pipeline on the Metal side. And indeed, we actually use all of them to some extent. Geometry shaders can be used to render particle systems. There's also a path which doesn't use them, which is used currently on Metal, because Metal doesn't have geometry shaders. And Metal does support some sort of tessellation, as far as I know, but I think it's kind of done through the compute shader. So the tessellation shaders can be used in the level editor currently in basis. So since we don't really support Vulkan in the editor right now, we don't really need to support the tessellation shaders, but I think they should basically just work, essentially. So let's try to make that happen. And the other thing that this shader program in Metal does is it creates this kind of vertex descriptor. So a vertex descriptor is essentially, let's have a look here. So create vertex descriptor. And you create a new one, you do it like this with the weird Objective-C syntax. And then we have this vertex format. And vertex format is that's a basis type. So we can use the same vertex format class in Vulkan as well. And so basically what we do is we iterate over all the attributes of the vertex format, and we get this vertex format attribute object to work with. And essentially what we're doing is we're describing to Metal and soon to Vulkan as well, what does the vertex format look like? So why is this tied to shaders? Well, it basically describes the input format to the vertex shader, right? So if we have a look at, actually we can go to the shader editor or the material editor. So here you have a vertex format. It can be, for example, the standard one is position, tangent, binormal, normal, text chord. And you have some others here to select. But if we go just with the standard one, and we go to the vertex shader, and we put an input here, you can see that this is what we get. Let's move that off to the side. You can see here that every word here maps to actually one of these guys. So position, tangent, binormal, position. Actually, the order is a bit different here. That's kind of interesting. But the order in this node doesn't actually map to the order found in the data. This format here specifies the actual data format. And I think actually if we do this, then oh yeah, this gets kind of a little bit off course now, but I think we should be able to see that. Yeah, now we have position and color. So this node here just it changes to just show two output pins. If we have just a single one, annoyingly it switches to that. You have just a single position here. So right, the vertex format essentially specifies what kind of data are we going to give to the vertex shader, and each attribute in here in this for loop essentially map to one of those nodes. And so that's why they are sort of packaged together with shaders on the code level. And VEZ has something similar. So let's have a look here. What was it called? Vertex input format. There we go. So vertex input format, and as you can see here, we have something that looks almost like the thing we had in Metal. We have VK vertex input attribute description. So that's one attribute. That's another attribute. Location binding offset format, and that looks pretty much like we have here. Format, offset, buffer index. Maybe there's a binding here somewhere or something. Yeah. But anyway, we should have all the data we need to actually create this stuff. So we're gonna create that as well. Right, I'm gonna move these off to the side so I can have a look at them when I do this thing. Let's go to Basis Shader Program VK. And right, so in a previous video, we mentioned that we actually already bundle a bunch of shader languages together into like a runtime shader resource. So we already have SPIR-V data there for Vulkan to consume, unless we have explicitly disabled SPIR-V generation for a specific shader or material. So we should actually have everything we need if we just simply give it a shader program description. Let's look at what we have in here. So shader program description has a bunch of per language data structs. And you can get per language data for a shader runtime language, and we have here SPIR-V. So we have source languages, HLSL, GLSL, or MSL. And then the runtime can be DirectX bytecode. That's what the D3D11 runtime uses. You can have GLSL, which we have commented out at the moment. We have SPIR-V, and we have actually MSL, which is produced from the SPIR-V. So currently we only use HLSL as the source language, and I would like that to remain the case. We also have DXIL, which I haven't implemented ever. I just put this here apparently at some point. This is like the newer version of the DirectX runtime format. And I could, in theory, I could have like pre-compiled metal types here as well. But you don't want to keep these, if you don't actually use one of these things, you don't want to keep them enabled here, because that would mean that the bin shader file gets larger. And like we can see here with the comment, I've commented this out because every bin shader file that we produce, bin shader is the runtime format for the basis shaders, and they all get this per language data. So you really want to actually use something if you want to have it in there. And per language data then has a shader code container for each of the shader stages that we have. So holds the source code of a single shader in source code or bytecode format. Right, so bytecode is probably what we will want here in this case, I think. But okay, let's just start fleshing out the class, and we can see what we actually have to do here. So I'm going to start by creating a function this time. Just looking at my other backends here off screen. So shader program description. We have this per language data that we just looked at. And in this case, the per language data is in fact SPIR-V. SPIR-V. And if you want to Google SPIR-V or haven't heard of it, it's essentially like written like this typically. It's like an intermediate representation of the shader instructions used by Vulkan and other things. And maybe we'll just, for good measure, we'll create the create vertex input format here as well. That was the thing that we just looked at earlier. We'll want to have both of these. And like so. And then we'll want to have, of course, the device VK. And we have a description. And these shader program descriptions they're pretty large. So we don't actually store them here. Large and large, all kind of depends. We're not typically talking megabytes, but still like many hundred K. So we only have a pointer to them typically. So that's fine. Let's keep that as it is. And then we have the actual shader modules. And in Vulkan, a shader module is this. It's a VK shader module. And in the metal one, we only had the vertex and the pixel, and then the commented out compute. Here we want to actually support all of them. So let's do shader type count. And shader type count is essentially 6, as you can see. So it's vertex, hull, domain, geometry, pixel, and compute. Compute is going to be in there, even though we don't even have a compute pipeline in the GFX API currently. So, but yeah. All right, and then I think we'll want to probably have the entry points as just strings. Might not actually need that. I mentioned earlier that I have actually modified VEZ a little bit. So typically in Vulkan you can't feed it GLSL. You have to feed it SPIR-V, and VEZ actually changes that, so you can just feed it GLSL and have VEZ then compile that into SPIR-V. I don't actually use that, so I ripped that part out. I put it behind a define in VEZ, and I always just feed it SPIR-V. And I'm not exactly sure if I need the entry points. You do need the entry points if you're using GLSL, but I might not actually need them for this. Right, so that should be enough for now. We need to actually count how many we are using. And then let's see if I can figure out the name of that other. So it was vertex input. That's vertex input format create info, but we probably vertex input format. There we go. Where is this guy? Where do you live? Huh. Right, that's like a handle. Okay. Okay, so we'll just keep a handle as well, and this is where we'll store the result of this operation that we'll perform in here, right? Okay. That looks all right. Maybe we'll put in these. Actually, no. Let's not do that. I was thinking of putting in the getters, but I think I'm actually just gonna go YOLO and comment out the private part there, and we can just access them directly. Too many getters in life. In life and programming in general. Okay. So this should be fine. I think this is a good start. I'm just gonna quickly look here at my other my other screen to figure out how to actually. Yeah. Okay. So let's start by just initializing these guys as always. So description is a pointer now, so we'll just set it to null, and we have shader stage count 0, and then we have this handle that we created. So that thing, that should be a vk null handle, right? And we'll probably need to go through these and initialize them to 0 or vk null handle actually. Shader type count and ++I, and we'll just do shader modules I equals vk null handle, something like this. Right. Okay. So I think there was a function called vec create shader module. Yes. Here we go. And so this takes a device. It takes a vec shader module create info, and it essentially returns a shader module for you. That's good. That is what we want. Okay. Cool. So now we can go into, I guess, create shaders. So this is where we'll get the actually, yeah, let's just do this in order. So we get the vertex format. I would assume that's part of the base class. Yeah, GFX API shader program. Okay, so that's fine. We can keep that. We want to do like a GFX API shader program description per language data, and we call this again spr-v, and just do m description get per language data and type spr-v. And then we need to actually make sure that the spr-v is enabled. So trying to load a Vulkan shader which contains no spr-v code. Like, that's not a good thing. Let's not do that. So then we can create the shaders with spr-v. And we can also call this other thing, create vertex input format. Cool. And I think actually the destruction should be pretty simple. Maybe we can do that. Let's just do this in order once again. So create shaders. Okay, so we'll start with shader count of 0. And then we do like for shader type count. So shader type count, what is that? That's 6. Okay. Yeah, that's probably fine. Okay, so for uint I equals 0, I is less than shader type count, not compute, but count. And then we can simply do entry points I is before we do this, actually, we don't necessarily have all of them. Let's do GFX API shader program description, and we have this other struct which we looked at, which is called shader container. We just call that code something. So spurv code containers. So this particular code container. So that's code, and if code is enabled, right? So if essentially this shader stage has enabled code, then we can do code dot entry point. That's a string, right? And that's a string. Yes, okay. Okay. And now I remember something kind of weird from my previous journey with Vulkan. And that is the fact that this code thingy here, this is, even though this is binary, this is actually given as 32-bit aligned content. Let's see. So what was it? P code. That's not the thing. That's not the thing. We have. Can we find this here? Yeah, we can find this here. So yeah, since the since VEC is sort of designed to work with GLSL, they just do something like they read a file into a string and then they pass it to the create info and set the entry point and blah blah blah. We don't do any of that. We just have the spurv ready to go. So we need to do that a bit differently. So how do we actually do it? Like we have the bytecode here in the shader code container, but this is not. This is just a binary array. This is not going to be 32-bit aligned. So I guess we'll have to do that ourselves. So code aligned, and let's do something like new array. Nope, not new aligned. Even though we could I guess use that as well. But let's do this, and then let's do. So we have code. We have the length, right? Bytecode length divided by 4 plus 1. And allocator type would be mem allocator GFX API. Right. And then we would mem copy into code aligned. And the size is size of 32. I'm gonna get this wrong probably. So it's code length, bytecode length. We have that thing again, right? That is, yeah, that is the size of the buffer. And we have code bytecode. We have code bytecode length, right? Something like that. I might have to actually come back to this if this doesn't work, but allocate the GFX API. Right, so we allocate the required amount. Take the code in the bytecode code, copy it into the aligned. Yeah, it's a bit weird. Some of this I've taken from an old Vulkan tutorial, which showed me how to do something like this. I think that's how I've done it before. So let's use that and see what happens. So we have VEZ shader module create info, which we call create info. And what does the create info want? It wants the stage. Okay, so create info.stage is, and then we have get stage flag bit. Yes, this is the one we want. Again, from the conversion functions, GFX API shader type, isn't it? Yes, it's shader type, and then we turn the index into that. Let's make sure we got that right. So that's a shader type. This returns a VK stage flag bits, and it's the thing that this guy wants. So that's good. Okay. And that's good. That's good. The code size. That would be. That's a size T, and what is that? Oh, that's a size T as well. So it's just code.bytecode length. And then create info.pcode. And this would then be the code aligned. And create info.pEntryPoint. This would be entry points I. And this is why I put it in a string like this, so that I don't know if that's actually that probably wouldn't need this, because I would assume this guy is gonna die, and then the pointer to this is gonna be valid as long as this guy needs. But whatever. It's a few strings. It's fine. Okay, and then VK result, and what was it called? VEC create shader something? No. Create shader model. There we go. Why did it not actually work? And that would be the address of create info. And this would be the address of M shader modules I. Like so. And then we can take one of our trusty asserts and plonk it down. And that's that. And then we can increment our shader stage count. Let's not forget that. Okay. The reason, by the way, why this it highlights some of these is that it's unhappy that some of these enums are unscoped. It's like the most stupid warning ever, in my opinion. And of course, it's complaining about the Vulkan SDK. So it's like, well, what do you want me to do about it? But oh well. Let's see if this works, or let's see if it builds. First of all. And if it builds, then we can perhaps put in the destruction of the shader stuff, and then actually try to run this and make sure that it actually succeeds. Actually, let's just try that now. So if we run this, we should be creating shaders almost immediately. Yes. Let's see incidentally which shader are we creating. So shaded program resource, we'll actually get a file name here. There we go. So it's mesh shadow map. It's the basic shadow map shader that we are creating. Okay, and that guy should have probably pixel and pixel and vertex. Yeah, so here's the vertex shader. Then we have some empty stages. We have a pixel shader. Yes. Looks good. Okay. So we go in and we actually... Hey, success. That's cool. Then we skip 1, we skip 2, we probably skip 3, and then now we should go in again. And look at that. Okay, so this thing actually worked then. Fun. So we can create shaders. Now we should destroy shaders. So we need to get rid of them here. And if we have a create shader module, it only is logical that there would be a destroy shader module function. Yay. Okay, well, let's not get ahead of ourselves. So yeah, I think what we can do here is simply we can do this, and then if m shader modules I is not vk null, then we can destroy it, because like we initialize them to vk null here. So that is good. That is good. And we can call vez destroy shader module m device vk get vk device, and we do shader modules I, and then we can set this back to vk null, just because it's good practice to do that. Right, and we can even, if we want to be really fancy, we can even do entry points I clear those strings. Okay, then we can do shader stage count is 0, and I'm getting a little ahead of myself here, but maybe there is like a shader destroy vertex something or other, right? Vertex format, yes. So we're going to want to destroy that format that we'll be creating next here. So let's do that, because it's easy, and we can simply give it this, right? That should be it. And both of these should return void, so there's no need to actually check anything. Yes. Okay. Cool. All right. So onto this guy then. I was thinking I would cheat a little bit and just copy paste this over from the metal side. How about that? Because well, it's yeah, it's a little nasty. It's a little nasty. Maybe the D3D. Where do I do this? Do I do it in the shared program as well? I think I do. Yeah. Yeah. Well, maybe we'll just actually do this properly. So let's do like a bottom-up approach this time around. So we'll take like that, and what we actually want to do here is we'll want to have the opposite function of this. That would be vez create vertex input format. Take those guys away. And what do we need here? What do we need? Well, we need a create info. Create info as usual. So let's use that as the second one, and then of course we do that. Right. So that is essentially what we want to do. But now we need to fill in this guy, and yeah, this is where it gets a bit verbose, if I remember correctly. So you essentially give it input bindings and you give it input attributes. So an input binding description list and an input attribute description list. So let's add a couple of vectors for those. So vector of right, so it's using just the normal Vulkan types here. So input binding descriptions, right? And we have this one, which would be vector to. Why do you put a space there? That's annoying. This would be attribute descriptions. What? Attribute descriptions. Okay. So now we have somewhere to store these guys, and in fact we can probably just take this now here and do like vertex binding description count, and this would be a uint32 binding descriptions dot size, and we can do the actual p vertex binding descriptions, right? So it was that one, and this would be this one. Let's make sure I haven't gotten those mixed up. Yeah, so that's that one, and that's the next one. And then we have this one, create info dot, and we have the same kind of deal, but we use this other vector for this. And that would be the, oh, nope, no. Right. So binding count, bindings, attribute count, attributes. Okay. That looks good. So, now we just need to fill these in, and then we have like the whole thing there. And how the hell do we do that? Right. Okay. So. Yeah, so I'm looking at my metal thingy here on the other screen. How I have done this, so like it loops through the vertex attribute format, vertex attributes, layout index. If the index switches, then we push the previous one. Yeah. Okay. Well, let's take the for loop, because we'll want to iterate over these guys. That's for sure. And then, what do these guys actually? They have a binding, stride, and input rate. Okay. Straightforward. Location, binding, format, and offset. Well, geez. Yeah, this requires some thinking. Other attribute. Right, I'm gonna have a think about this, and I'll be back in a sec. Okay, seconds up. So this is what I came up with. I had to think about it a little bit. So, right, let's go through what I did. So we iterate over the attributes, right? And we get the current attribute, and I have this previous input slot here, which is initialized to like this invalid value. And if it is the invalid value, then we encounter the first attribute. We create a binding description, which we store there, and then we keep essentially track of it, like what are we, where are we binding, and then we fill it out. So is this like a vertex or sorry, like an instance or vertex attribute per instance or per vertex? And then in subsequent iterations, if we have encountered something previously, so this is no longer this invalid value, then we check if it has differed, and in that case we push the binding, and then we set it up in the similar way. And before we talk about the attribute, this means that when we exit this loop, we will have essentially a binding ready to be pushed still. It might be the only one if we never got here, or it might be just the last one if we have pushed previous ones. So that's that. And then the attribute is kind of simple. We just fill it in. We get the slot in attribute input slot, and the location, and the format, and the byte offset, and we push it to this guy here. And I did test this, and it does seem to work. So we can quickly have a look here and see what's what. And so what is? Let's have a look at our watch window, or locals window, perhaps. It's easier. So the input is the M vertex format. So we go to this, and we go to, come on, like, there it is. Okay, so we have 5 attributes: position, tangent, normal, binormal, position, tangent, binormal, normal, text chord. And so this is what the data looks like as it comes in. And then what we have now in our locals, you can see that we have 5 attribute descriptions. They all look, the formats look like they make sense. Like we had position, then binormal, normal, tangent, and then the UV. So position and the normals, they would have 3 floats. They're 3D vectors, and then the UV is the text chord is the last one. It would be a 2D vector, so it has only 2. That makes sense. Location 0, location 1, location 2, that works. Binding is still 0. And the offset increases with every attribute, so that's fine. And then here we only have 1 input description. So binding and the stride for the whole thing is 56. And we're pushing vertices. So this kind of looks like it would work. I don't know, do we actually ever get here? Now, first of all, we can make sure that this actually does succeed, and it does. Do we actually ever get, do we have anything with multiple bindings? Maybe not. Oh, the timeout to my resource server probably. expired. Right, so we don't actually ever get there, but that makes sense. I know my data well enough to say that that's probably exactly how it is currently. Okay, so that's good. So now we have this, and now it should be very, very easy to actually use a shader, because we have the modules here, and we have the input format there, and those are the things that VEZ wants us to have at hand. So this was a bit longer, at least for me, when I put together that vertex format, but I think it turned out pretty nice. So now we are actually rapidly approaching the point where we can actually put things on the screen, and that is wonderful. So we have the pipeline is probably the next thing to do, and then after that the render context, and this guy is going to be a big one as well. So things to look forward to. Remember to like all the buttons and hit all the buttons and the bells and everything. And I'll see you in the next one. Bye.